Okay, let us start our seminar now. Our speaker is Professor Noumi from Tokyo. Yes, you can start.
Okay, thank you very much for the invitation. So today I will talk on the title, Elliptic van Diejen difference operators and elliptic hypergeometric integrals of Selberg type. And today I have only something like 10 pages of slides, so I think I will go slow as possible. And in this talk, I will discuss some class of eigenfunctions for the so-called elliptic van Diejen difference operators. And I don't know what is the most appropriate word for this class of eigenfunctions. Maybe they should be called singular solutions, singular eigenfunctions, because they appear only when the coupling parameters satisfy some kind of constraints. Okay, so actually I will discuss some class of eigenfunctions and which are represented by elliptic hypergeometric integrals of Selberg type. I will explain later what they are. And also they are constructed from simple seed eigenfunctions by iterated application of integral transformations and thanks to the gauge symmetries and kernel function identity. So there are two, in here I quoted two papers, and the second paper, Atai Noumi eigenfunction, blah, blah, the second paper appeared recently in Advances in Mathematics. I think I will explain the essence of the content of this paper today. Okay, so if you have any question, please interrupt me anytime you like. So I first start by recalling the Ruijsenaars operator and van Diejen operator in the elliptic case. But before that, I recall some basic things in the trigonometric case. And in this talk, I denote x, which is x1 through xm, and the canonical coordinates of the algebraic torus. Algebraic torus means m copy of the C star. C star is C minus the origin. And so I fix some parameter always qt to parameters, assuming that the absolute value of q is less than 1. And I also use this. Do you see the pointer here?
Yes, we see.
Yes, we do.
So this t sub qxi, I denote by symbol the q shift operator in the variable x. So it multiplies the variable xi by q and leaving other variables unchanged. And so I wrote here the MacDonald operators in the trigonometric type A case. So dx is a summation of this type of q-shift operators. It's a q-shift operator of this form. And here you have a coefficient, aix semicolon t is defined by this rational function. So in the numerator, you have 1 minus dxi over xj, and in the denominator, 1 minus xi over xj, where j runs over the index, which is distinct from I. So it is not obvious, but this operator acts on the ring of symmetric Laurent polynomials. And there you can try to diagonalize this operator. Then the eigenfunctions are the so-called MacDonald polynomials. So this is a very well-established fact. And also, this system is known to be completely integrable. completely integrable in this case means the existence of commuting higher order operators, which are algebraically independent. And so this complete integrability was already established around 1987 or 1988 by MacDonald and Ruijsenaars independently. Okay, this is the A-type case, but the Van Diejen difference operator, which I'm going to discuss today, is related to it's an elliptic version of the Cohn-Winder operator, BC type case. So this Cohn-Winder case, you have 4 parameters, A0, 1, 2, 3, and you consider this type of Q difference operator. And here you have A coefficients, AI plus and AI minus, and also you have shift operator -1 here, and shift operator inverse -1 here. And the coefficient is given in this form. So this part is related to the root system of type BC. And so the first half of this part is the same as this an A-type case, but you also have a factor like 1 minus t times xi xj. This is a D-type root, so to speak. And in front, you have a rational function of this form, and degree 4 or in the denominator and also in the numerator. So you have 4 parameters here. So if you know about our one variable case is this Q difference operator describes the Q difference equation for the so-called Askew-Wilson polynomials. And so in the case of Askew-Wilson polynomials, you may use the symbol A, B, C, D. There are 4 parameters besides Q and T. And so this is a many variable version of the Askew-Wilson operator, which was introduced by Cohn-Winder. It was around 1992 or 3, I'm not sure. But this operator, D sub x with parameter A semicolon qt, acts on the ring of invariant Laurent polynomials. Invariant means this you consider this this is let's say octahedral hyperoctahedral group of degree m, which is a semi-direct product of plus minus to the power m and the symmetric group of degree m. And this symmetric group of m acts on the variables x1 through xn, permuting the variable indices of the variables. And this part takes care of the inversion of xi to xi inverse. And so in this case, also, this operator acts on the Wm invariant Laurent polynomials. And there you can try to diagonalize. Then you have a basis of this invariant ring consisting of eigenfunctions of this operator. So they are called Cohn-Winder polynomials. So the Cohn-Winder polynomials are multivariable version of Askew-Wilson polynomials. And also this operator also has higher order commuting operators, which was explicitly given by Van Diejen around 1994. I will not recall these higher operators, but today I will just use this first order operator. These are the 2 important Q difference operators in, I would say. So this is kind of, so you are, in the physical term, you are working on a one-dimensional quantum integrable system of Calo-Zero Sutherland type. But you are working, we work on the difference version or relativistic version in the terminology of Ruijsenaars. Okay, so we consider the elliptic version of these things here. And okay, so I now move on to the elliptic version. So I first fixed the so-called elliptic norm P, which is also have absolute value less than 1, and consider this elliptic curve. And so important building block is the elliptic theta function. This is Jacobi's, essentially Jacobi's elliptic theta function, but I use the multiplicative notation. And this is a standard notation of P shifted factorial, infinite factorial. And this defines the holomorphic function on in Z. And by combining two of these P shifted factorial, Z with the argument Z and P over Z, I denote by this function, by this symbol, theta of CP. This is the multiplicative notation of the Jacobi theta function. This is up to some power function of Z. This is equivalent to the odd theta function, odd one of the Jacobi theta function. For Jacobi theta functions, there is only one odd function. So this is something. Yes. If you multiply Z to the power minus half to this theta, then it is essentially the odd theta function of Jacobi. And maybe there are many conventions of theta function, but if you multiply P semicolon C, P sub infinity, so giving the 3 infinite products, then it has a very nice Laurent expansion of this form. This is the Jacobi triple product identity. And so probably this formula is sufficient if you wish to, I would say, identify this function with elliptic theta function you are familiar with. And if you multiply the variable Z by P, then from this theta function, you get the factor minus Z inverse. This is the quasi-periodicity of this elliptic theta function. And also, this is kind of inversion formula. And this function is invariant with respect to changing Z to P over Z. And also, from this expression, you can pick up the first factor, 1 minus Z. Then the other factors contains P in front. So when P goes to 0, this theta function goes to 1 minus Z. So this is the trigonometric limit. So the basic approach of to how to say, make going to the elliptic world is to replace, if you have an expression 1 minus Z, then you can replace this with the this elliptic theta function. And also I use another important function, elliptic gamma function, Ruijsenaars elliptic gamma functions. And in this case, you have 2 bases and a double shifted product, PQ shifted products, an infinite product like this. And take the ratio of this form. In the denominator, you have argument Z, and in the numerator, you have a PQ over Z. So this meromorphic function is written in this form, gamma Z semicolon PQ, and this is called the elliptic gamma function. So the reason that we call this elliptic gamma function is the following. So if you multiply the variable Z by Q, then from this function, this elliptic theta function pops out. And so since this function is symmetric with respect to PQ, if you multiply the variable Z by P, then you will get the factor theta of Z with base Q. And also, this is an inversion, which is obvious from this expression. And also, so as I said, P goes to 0 limit is the trigonometric limit. So if the parameter P goes to 0, so the numerator disappears, and this denominator becomes the Q-shifted product of this form. So what you have in the trigonometric case, if you have a trigonometric, this expression, 1 over z, okay, I would say reciprocal of this z semicolon q infinity will be the trigonometric limit of this elliptic gamma function. So in the elliptic setting, you will see in many places that this type of q-shifted factorial is replaced by the elliptic gamma function this way. And also, it is interesting to see if you take the limit, before taking the limit p, as p goes to 0, if you can multiply the variable z by p, then this expression becomes this way. And if you take the limit when p goes to 0, then in this case, the denominator disappears, and the numerator becomes this symbol. And so this shifted factorial and this shifted factorial both appear from the elliptic gamma function. That is something more or less what you need to understand the elliptic version. So I first consider the so-called MacDonald elliptic version of the MacDonald operator, which is called the elliptic Ruijsenaars operator. Then I'm using the calligraphic symbol d sub x, and with this coefficient ai. So in this case, you have this expression of theta function. So as I said, if you go back to this if you have 1 minus t xi xj, and you please remember that you have 1 minus t xi over xj, and 1 minus xi xj. So in this elliptic version, 1 minus t xi xj is replaced by this theta function, and like this. So naturally, if you take the limit when p goes to 0, this goes back to the MacDonald operator, which have MacDonald polynomials as an eigenfunction. And already in 1987, Ruijsenaars, there is a famous Ruijsenaars paper who established the complete integrability of this operator. I mean, so there are commuting family of Q difference operators, including this dx as the first order operator. And there are m independent, algebraically independent difference operator. So this is a complete integrability. And so the main goal of considering this type of elliptic difference, Q difference operator, is to completely understand the structure of eigenfunctions. But so our knowledge on eigenfunctions for the elliptic difference, Q difference operators are very limited. But I wrote some papers with Langman and Shiraishi, and I discussed some class of eigenfunctions which can be expressed in terms of power series of P. And there you can also have an elliptic version of MacDonald polynomials and other eigenfunctions. So if you are interested, please look into my paper for this for. I have a list of references in the last page. So afterwards, you can see the reference later. Okay, this is the A-type case. And BC type case, you now have 8 parameters, A parameters, A0, A1 up to A7. So in the trigonometric case, you have 4 parameters, but in the elliptic case, number of parameters are doubled and to 8 parameters. And so you have 8 parameters besides P and Q and T. So, and the first order operator takes this form. And now you have a TQXI and the TQXI inverse here. And in front, you have some coefficient here. And also there are zeroth order term like this. So in some sense, the point operator can also be written in terms in that form. If you take this zeroth order term is the minus of this thing, a plus I and a minus I. But so in the elliptic case, the coefficient is this written in this form. This is very similar to the Cohn-Winders operator in the sense that the 1 minus z is replaced by theta of z semicolon p. But here you have eight A parameters and instead of 4 parameters in the Cohn-Winders case. But other parts structure is otherwise the structure is the same. And I did not give an explicit formula for the zeroth order term. Actually, the zeroth order term, this A0 is very complicated, and which can be characterized by some kind of quasi-period. Actually, this part is elliptic function in each variable xi, and this function can be characterized in terms of the position of poles and the residues. But I will not use the explicit formula here. So, but anyway, this is a form of the elliptic van Diejen operator. And actually, complete integrability, existence of commuting family of higher order Q difference operators was established by Komori and Hikami. I'm not sure this was the first, but yeah, around the late 90s, Komori and Hikami constructed some higher order, showed a way to construct a higher order commuting family of Q difference operators for this. And but our knowledge about the eigenfunctions for this elliptic van Diejen operator is very limited. So but what I'm going to talk is to propose some class of eigenfunctions, very special eigenfunctions. So we do not have much, have not established the existence of sort of eigenfunctions that form a complete basis for an appropriate function space. But that is, we are very far from that kind of completeness of eigenfunctions. But still, I think some singular special existence of singular special eigenfunction will be important as at least the first step of understanding of eigenfunctions. Okay, so I first remark there are some special eigenfunctions expressible in terms of the Ruijsenaars elliptic gamma function. Before this, I like to comment that the constant function 1 is not always an eigenfunction, but the constant function 1 is an eigenfunction if these parameters satisfies the balance, the so-called balancing condition like this. Product of A0 through A7, product of all A parameters times t to the power 2m should equals to PQT squared. And this condition is equivalent to saying that if you look at the quasi-periodicity of this function, coefficient function, so these A parameters satisfy the condition I just mentioned, then this function becomes elliptic function. Elliptic means a p-periodic function in each variable, in all the variables. So then in that case, if you apply 1 to this apply this operator to 1, then you have to consider this summation of these things, dropping this t and dropping this t. These ai and ai plus and ai minus and a0. Then they are elliptic functions in each variable. And if you look at poles, position of poles, and if you check the residues all cancel, then you can conclude that it's a constant. Then you can say that the constant function 1 is an eigenfunction in that case. So this is how you need some balancing condition to get the actual eigenfunction. Here's an example, first example. And also there are some eigenfunctions which can be written in terms of product of elliptic gamma functions, just like this. Oh yes, so if you consider the hypergeometric function case, so ordinary Gauss hypergeometric function, there are the power functions x to the power something, x minus 1 to the power something. This type of thing is a very special case of a hypergeometric function. And in some sense, this elliptic gamma functions is more or less the same kind of eigenfunctions, same as similar nature, similar to the power functions. But anyway, so if you can, let's take a subset of indices in the index set for the A parameters and assume that this cardinality of K is even. Then if you can form this product of 1 over elliptic gamma functions in this way. Then if this the parameters, A parameter satisfies this balancing condition, a bit complicated, but product of AS belonging to with S belonging to K and with not belonging to K, you have out there. So you need some balancing between the two products of here. Then under this type of balancing condition, you can show that this function U sub K is an eigenfunction. So this is one class of seed function and seed eigenfunction. And also another type of, there is another type of eigenfunctions, which is in fact the product of elliptic gamma functions. This one, so if you take this combination and if you assume this balancing condition like this, then you can show that this is an eigenfunction for the elliptic van Diejen operator. So I will explain later why you can see these, how you can see these functions are actually eigenfunctions of this van Diejen, elliptic van Diejen operator. But please notice that every time we discuss eigenfunctions, we need some balancing condition, and it's a constraint on the coupling parameters, A parameters and PQ and T. Okay, so this is a class of eigenfunctions expressible in terms of elliptic gamma functions. So now I go to the elliptic hypergeometric integrals of Selberg type. So the original Selberg integral, which was found in 1942, a long time ago, is this one. So probably many of you already know Selberg integrals, but it's a so in this integral, you have a number of integration variables n. And so here you have xi to the power alpha minus 1, x minus 1 minus xi to the power beta minus 1. This is a kind of multiple beta integral. But besides this, you you put here in the integrand the power, complex power of the difference product like this. So if this power parameter gamma is 0, this is just a split into a single integral, and it is just a product of beta functions. But even after introducing this parameter gamma, so this dependence of the integral on the parameter enters very nicely into the argument of the gamma function. It's slightly complicated, but you have this explicit expression in terms of ratio of products of gamma functions. Okay, so there are many variants of Selberg integrals, variation extensions of Selberg integrals. So what we are going to, yes, one of the extension of Selberg integral, one of the standard, there is a standard Q-Selberg integral called the Gustafsson's. This is not the only Q-Selberg integral, but anyway, Gustafsson's Q-Selberg integral is standard in some sense. And as in the case of Askew-Wilson or Cohn-Winder, you have 4 parameters, A0, 1, 2, 3. And you consider this integral. This time, this is a contour integral on the real torus, n-dimensional torus. And maybe it is not obvious, but this combination, oh yes, I think I should say, explain. I'm using this plus minus double sign symbol, but this is an abbreviation of a product of 2 factors, 2 shifted factorials, xi squared semicolon q infinity times xi minus square minus 2 to the power minus 2 semicolon q sub infinity. So I frequently use this double sign notation referring to the product of how to say, products of factors with different signs. So in this sense, in the numerator, you have 2 times n infinite product here. And then here you have, this is also a product of 2 factors. So 4 times 2 times n q infinite products like this. This part corresponds to this multiple beta part, beta integral part. And this part corresponds to this power of difference products part. This is although this is a BCN version. It's hard to say why this is good in extension to the Q integral case. But if you it is known that this integral can be evaluated, so in a very slightly complicated form, but so you have some q semicolon q sub infinity in the new denominator, and here comes 2 to the power n factorial. This is the order of the hyperoctahedral group of degree n. And here you have slightly complicated, but as I said, yeah, in some sense, in the gamma function and the infinite product have, how to say, the reciprocal of the Q infinite product, it takes the role, play the role of the gamma function. And this J gamma corresponds to this T to the power J semicolon Q infinity. And this gamma gamma corresponds to this part. And in the numerator, you have alpha beta with this I minus 1 gamma. Then in the denominator, you have product of 2 parameters, AK, AL, and with 2 T to the power I minus 1, very close to this form. So in the beta, ordinary beta integral case, you have alpha beta and alpha plus beta. But in this Q integral, since you have 4 parameters, so factors like this product of 2 parameters appear here, and the product of 4 parameters appear here. And also n plus I minus 2, you have the same number here. So you see the structure is very similar to the case of ordinary Selberg integral. It's very interesting. But anyway, so this function, this integrand, I mean this part, is very much related to the form. Wait a moment. Form of this. Sorry. どうやって戻るんだろう。Yes. Yes. This part is related to the coefficients of the Cohen operator here. But anyway, so actually, so no, you can this integrand of this Q-Selberg integral is the weight function for the orthogonality of Cohen polynomials. And actually, if you take this integrand as the weight function, then you can show Cohen-Winder's operator is self-adjoint with respect to this weight function. So that is how the orthogonality and Cohen-Winder's operators are related. Okay, so this is a Q version, and we wish to go to one step to the elliptic level. So elliptic version of the Gustafsson's Q-Selberg integral was found by Van Diejen's period of around 2000. And in this case, you have 6 A parameters, A0 up to A5. And the structure is very similar. But as I mentioned, elliptic gamma, you have elliptic gamma functions. But the elliptic gamma function corresponds to the reciprocal of the Q infinite product. So the role of the numerator and the denominators are interchanged here. But this part corresponds to power of difference product in the BC version. And so this is the this part corresponds to the beta integral part, multiple beta integral part. And here you have S runs from 0 to 5 and six parameters here. And so the integral is taken. This is a contour integral on the real torus. And if the parameters satisfy the balancing condition, a condition like this, it's called the balancing condition, then you can evaluate this integral in terms of elliptic gamma function. So you now have a P semicolon P infinity, P shifted products, Q shifted products, and this is the order of the hyperoctahedral group. And this part and this part, very similar, in some sense, very similar to the elliptic Selberg integral and Gustafsson's Q-Selberg integrals. So it is not easy to say how this is okay, so this is a Selberg integral. But if you, in general, you can increase the number of A parameters, A0 to AM minus 1. And then, so you can take this part corresponds to in the Selberg integral case, the power of linear functions depending on one variable. And so if you can consider this function. And actually, if you take the 8 parameters, A0 to A7, then elliptic van Diejen operator, you can show that this can be a sort of weight function for the elliptic van Diejen operator. And you can show that elliptic van Diejen operator is self-adjoint with respect to the integrand of the case where the number of A parameters M8. And I also discussed some determinant formulas for this type of elliptic hypergeometric integrals of Selberg type, of BC type with Ito. So if you are interested in please look into my paper with Ito, which appeared in 2019. Okay, so yes, then I would like to say that there are eigenfunctions which can be expressed in terms of elliptic hypergeometric integrals of Selberg type. So it's slightly complicated, but I'm using x variables for the m-dimensional torus and algebraic torus, coordinates of the m-dimensional, and the y variables for the n-dimensional algebraic torus. And in this case, y variables are the integral variables. So you have this product here. This is a power of difference products part corresponds. In this part, you have this type of linear, sort of linear factors like this. And I'm choosing, let's choose a subset of indices of A parameters with even cardinality. And if you form this type of product here. And here you have, this is a kind of kernel function of Cauchy type. And you have x variables and y variables here. And oh yes, this is plus minus means you have four possible here also, four possible combination plus minus plus minus. So this is an abbreviation of four gamma factors here. But if you define this function of x in this way, and if you tune the parameters bs here to be related to this a parameter, outer parameter here, like this, and take this c parameter like this, then under certain balancing condition on the a parameters, you can show that this psi sub 2 is an eigenfunction of the elliptic van Diejen operator for the a parameter. So this is this type of Selberg integrals called the type 2 Selberg integrals. And also there is another class of Selberg integrals, elliptic hypergeometric integrals called type 1. In this case, you don't have a numerator here, but other parts are very similar. And so in this case also, you have elliptic gamma functions with b parameters here, and here you have a kernel function with c here. And if you choose b parameters like this and the c like this, then this psi function defined in this way becomes eigenfunction of the elliptic van Diejen operator under the balancing conditions written in like this, expressed. So this is more or less the result I wanted to explain in this talk. And so maybe I used 45 minutes now. So from now I would like to explain how you can establish why these things provide eigenfunctions. And so there are two important important points in this construction. The one is the gauge symmetry of the elliptic van Diejen operator, and the other is the kernel function identity. So I begin by the gauge symmetry like this. So suppose you have a meromorphic function g of x, a, which can depend on a and qt, which satisfies this type of identity as the q difference operator. Maybe So dxaqt times gxaqt equals gxaqt and dxbqs. On the right-hand side, A parameter is replaced by B parameters, and the T is replaced by S. Or maybe I should, maybe I should have put this factor on the left-hand side, making it in inverse of putting the inverse of G here. Then this means that by conjugating this elliptic van Diejen operator by this gauge function G, so you obtain the same elliptic van Diejen operator, but A parameters and the T parameter are replaced by B parameters, other parameter B called B, and other parameter called S. So there are some functions G that transforms elliptic van Diejen operator to other elliptic van Diejen operator with different parameters by conjugation. So if this type of thing, this identity holds, then suppose that the phi of x bqs is an eigenfunction of this operator on the right-hand side. Then you can multiply this gauge function and call it psi. Then you can show that the psi is an eigenfunction of this van Diejen operator with AT parameters. Okay, so it's very simple. So suppose that this phi function satisfies this eigenfunction equation and multiply this G. Then from this commutation relation or conjugation, since the conjugation of D gives dx with A parameter, AT parameters, gives B the same operator with parameter replaced by B and S. So from this relation, you immediately see that this psi function obtained by multiplying G is an eigenfunction of the van Diejen operator with AT parameters, right? But the eigenvalue unchanged. So yes, so the function I showed when I explained the eigenfunctions which are expressible in terms of elliptic gamma function, I introduced this function u sub k. Actually, this is a gauge function in this sense. So by taking this type of product with k, by choosing some subsets of indices for A parameters with even cardinality, and consider this function defined in this U function defined in this way. Then by conjugation, elliptic van Diejen operator with A parameter is transformed to the elliptic van Diejen operator with B parameter with B so the sum of the parameters, sum of AS, an index for indices S belonging to K, the A parameter is replaced by PQ over AS inverse. So this is the this is a gauge symmetry. This is one of the main gauge symmetry of the van Diejen operators. So every time you choose a subset of indices in this indexing set 0 to 7 with even cardinality, you get this kind of gauge transformation. You have this gauge transformation. So this type of parameter change can be regarded as a reflection with respect to some roots of type D8. And actually, these gauge symmetry gives rise to symmetry of the elliptic van Diejen operator, which is isomorphic to the wire group of type D8. So Van Diejen operator have WD8, D8 wire group symmetry as its nature, and this is one type of gauge symmetry. Okay, so let's look at this gauge symmetry here, and suppose that the B parameters satisfy the ellipticity condition. Then consider the special case where the B parameters defined by this satisfy the ellipticity condition, so that the constant function is an eigenfunction for this operator. Then if you apply this operator to 1, so then it implies that the UK, from this principle, and the B, so phi, if 1 is an eigenfunction, this part of phi is 1, and so then the co-gauge function, psi is equal to the gauge function. So the gauge function is an eigenfunction if this B parameter satisfies the ellipticity condition. Okay, so from this gauge symmetry, you see that so B parameter satisfies the ellipticity condition, then UK is an eigenfunction. So let's go back to the statement. I explain. Yes, wait a moment, please. Oh yes. So I explained how this statement, this combination of elliptic gamma function is as I said, if this parameter satisfies some balancing condition, this is an eigenfunction of this elliptic van Diejen operator. But this statement follows from the gauge symmetry that I explained right now. So from this gauge symmetry, and so if the B parameter satisfies the ellipticity condition, so constant function 1 is an eigenfunction of this operator. So this gauge function is an eigenfunction of the operator, or operator with a parameter. So that was how you can prove. That is how you can prove that the first statement, the statement I mentioned earlier. So there is another gauge symmetry here. So this is a half of the weight function corresponding to the power of difference product. And then you can also show that by conjugation, this conjugation by this function V transform the elliptic van Diejen operator to another one with T parameter replaced by PQ over T. So there are some, as I explained, so there are several gauge transformations that transform the A parameters in the elliptic van Diejen operators. So in this case also, if this AQT satisfies the ellipticity condition, then constant function 1 is an eigenfunction of this part. So then this V function is an eigenfunction of this operator with a parameter. So that is how eigenfunctions expressed in terms of elliptic gamma function arise from the gauge symmetry. Okay. Now, next thing I would like to explain is the kernel function identity. This is related to the Selberg type integral. So, I wrote a paper with Komori and Shiraishi a long time ago. It's 2009 paper. Using the coordinates, x coordinates for the m-dimensional torus and y coordinates for the n-dimensional torus, and you consider two sets of variables. and consider the function of x and y defined in this way in terms of the elliptic gamma function. Here you have xi plus minus yj plus minus. So there are 4 factors. And with some constant like this, pq to the power half and t to the power minus half. So this is a kind of, I don't know, but if you are familiar with Macdonald theory, Macdonald polynomials have a so-called a Cauchy type kernel. And in the special case of sure functions, this is related to the Cauchy formula. So in some sense, this is this is this is related to this Cauchy formula for Macdonald's in the Macdonald case or Cohn-Wendell case. And so in the elliptic case, you can consider this function and regard this as a Cauchy type kernel, And so the kernel function identity, by kernel function identity, I mean the following formula. So this phi function is a function of x variables, which is m-dimensional, and the y variables n-dimensional. And regarding a function of x variables, you apply the van Diejen operator in x variables with parameter a, q, t. And on the right-hand side, you apply the same type of elliptic van Diejen operator on the y variables with parameter bt. And the bt, if you choose b parameters in this way, pqt square root of pqt times a over as in this way. So if the a parameters are b parameters are related in this way, then the results of applying the elliptic van Diejen operator with a parameter on the x variables and van Diejen operator in y variables with b parameter, they give the same result. This is called the kernel function identity under the balancing condition. You need to assume this type of balancing condition as well. So if you have this type of kernel function identity, you can use this kernel function of Cauchy type for integral transformation to form integral transform from the y variables to x variables. Okay, so suppose that phi of y in y variables with parameter b is an eigenfunction of with parameter b. So this is what you assume that here. Then, so you consider the integral transform of this function by using this kernel function, and also this is the weight function. So this is weight function is yes, weight function. Yes, weight function is the function you already saw somewhere. I'm sorry. This one, this type of thing. Here you have n variable, but this is the weight function for the van Diejen operator. So, sorry. Okay, so this is the weight function for which van Diejen operator is self-adjoint, for which is self-adjoint. And here is you have the kernel function. And if you take this type, if you consider this type of integral transform to define psi function in x variables and with a, and then you can show from this eigenfunction equation, you can see that you get an eigenfunction equation for psi with a parameters. So it is not difficult. Let's try this type of computation. So considering this integral, you apply the van Diejen operator in xa variables to here. It just go into the integrand here, and it acts on this x variables of the kernel function. But from the kernel function identity, this thing is equal to this thing. It's a result of application of van Diejen operator in y variable with b parameter to the kernel function. So this thing is equals to this thing. This was the kernel function identity. Then, as I said, the van Diejen operator is self-adjoint with respect to this weight function. It means that you can move this operator to this phi side. But since phi is supposed to be an eigenfunction of dyb operator, so this is a constant multiple of lambda. So this means that the result of integration psi gives an eigenfunction with the same eigenvalue. That's okay. So if you have a kernel function identity of this form, you can formulate integral transform that maps eigenfunction in y variables with certain parameter to eigenfunctions in x variables with other parameters. So this gives an integral transform that maps eigenfunction to eigenfunction. Possibly the parameter should be changed. So what to summarize, this is more or less what I want to explain today. But starting from seed eigenfunction, one can generate a class of eigenfunctions applying repeatedly the following two procedures. So you can apply the gauge transformation by using the gauge function UK or a V function. And also integral transform with the kernel function phi of Cauchy type. There is another kernel function, but just this explanation will be sufficient today. So let's go back to. So, for instance, in this case, it is not so easy to explain, but you apply some gauge. Yes, you consider that constant function is eigenfunction for some van Diejen operator. Then you can apply U sub k gauge function. Then because the result of gauge transformation, you drops out the gamma factors with index belonging to k. So this part is how to say made smaller, and then this part is a Cauchy kernel. So maybe it is not very easy to see, but this is this function, this eigenfunction is obtained in two steps. So first, start constant function 1, and you gauge function. You apply the gauge symmetry, and then you can see that the U sub k function is an eigenfunction. Then, so to that eigenfunction, you apply the integral transform by the Cauchy kernel. So then write down everything. Then you get this type of integral representation of an eigenfunction, and it is actually a kind of a Selberg type integral. So, but as I mentioned, every time you apply the kernel function identity, or when you assume that ellipticity condition, so that the constant function should be an eigenfunction. So every time you need some constraints. So that is a very typical. Every time you apply integral transformation, you need to add a constraint, and so balancing condition, called a balancing condition on parameters. So this is a sort of characteristic feature in this construction of eigenfunctions. Okay, 1 hour and a half. Okay, that is more as I wanted to explain in this talk. So in the last page, I included some references. So maybe you can look at this PDF later. Okay, thank you very much.
Okay. Thank you for the so interesting talk. Any comments, questions? Toля.
Can I ask you a question? Masatoshi-san, okay. It's Volodya Rubtsov is here. Do you hear me?
Yes, yes.
Yes.
Probably it's a very superficial question, but do you have some relations between your integrals and hypergeometric period integrals of Terrasoma?
Terrasoma?
Yes. Period hypergeometric integrals are monotype or...
Oh, yeah. Yes. This is in the ordinary hypergeometric case, you have a product of linear functions and yeah, you can say integrals of products of linear functions, right? Yeah. Aomoto type or Gelfand type.
Yes, initially, yes.
Yeah, so, but after that, you can also consider the Q integrals, Jackson integral version, or a contour integral version like Valchenko, Tarasov. But we are coming to the next, we go up to the next step, elliptic version. So, okay, so
you expect some relations with the period integrals, I suppose.
Oh, yes. Period integrals. I'm not sure, but wait a moment. So if you see, this is the typical situation here. This part corresponds to the power of difference product, and this part corresponds to the power of linear functions. But we are dealing very special case, not general. But so if you can take an appropriate limit, first go to the trigonometric and to go to the Q equals 1 limit, then that should be, you should go to the differential setting to recover Selberg type integral, ordinary one. So it's related to Aomoto's integral, yeah. It is not so easy to directly take the limit, but in principle.
It is not so evident, but I suppose that there is some relation this elliptic Selberg type integral and some period integrals.
Yes.
If you look the measure, it is absolutely the same measure, but the function in front of this measure should relate somehow to in the simplest case to some to some super potentials in Landau-Ginzburg models. So it is a kind of elliptic.
So, yeah, it's hard to say.
It is some kind of surface like product. I mean, this factorization, of course, should be interpreted in proper way, but it looks like. You know, it is difficult to relate the say in the picture of elliptic Penlevé equations. It is very difficult. I mean, elliptic Q Penlevé equations. Eric Rein's type. It is very difficult to recognize the avatars of monodromy surfaces of usual Penlevé systems. So maybe these formulas, they are some avatars of Landau-Ginzburg surfaces.
Maybe so, but I don't know how precisely you can relate these things to Wow, I don't know.
It is interesting.
But
I think the Terrasoma formula should be a kind of bridge between this, but
Terrasoma's determinant formula? Or?
Okay, it is finished discussion. Okay, Masatoshi,
Yes.
I want to ask you, okay, there are many generalizations of integral, for example, Selberg type integral, for example, by Marchenko J-free analog of Selberg type integral. But this is not my main equation. My main equation is because this is construction for DC, and that means it is construction for symmetric group, semi-direct product of symmetric group and cyclic group of order 2. What happens for complex reflection groups? Is it known something for complex reflection group which corresponds to extension of symmetric group by cyclic group or any order? However, some elliptic, where is part of extension of McDonald theory? But is it possible to extend something elliptic extension in elliptic direction?
I don't know. Sorry, I don't know. Sorry.
Yes, I mean, because some kind of McDonald theory, really one of the interpretation of McDonald theory, really based on algebra.
Yes.
Theory,
oh, yes.
Of this theory for your theory, elliptic theory for other types, other finite Y groups, for example, for Diejen or.
I don't know. So.
Okay.
You can define kind of elliptic version of the McDonald constant term or something like this.
Yes.
But for associated with root systems by using elliptic gamma functions. But the structure seems very different, and A-type case and BC-type already. I don't know, but
of course, structure of algebras group is very different.
BC-type case is the only thing we can actually manage to understand, and I don't know what is happening on the other root systems. It's an open question. I don't know. We don't know yet.
Okay.
Can I ask a brief question also about the last kernel formulas?
Kernel?
About the kernel formulas, the last brief question. Do you have some multiplication formula for eigenfunctions?
This one. Yeah. Kernel formula.
Yeah, but I mean, do you have a formula for products of your eigenfunctions, for your phi? In different points, y and say and x. Say phi of x times phi of y in terms of your kernel.
Phi of x.
Some nice.
I don't precisely understand what you mean.
You have some eigenfunctions, yes?
Yes.
And we should expect, like in the classical case, that you should have a nice product formula.
Oh, a product formula.
Yes.
Like McDonald case, P lambda and P mu.
Yes, like in Legendre classical product.
Oh, yeah. So it's a very good question, but we are very far from that level. So we do not have.
But your kernel should give you some hint how to do it in compare with classical case.
Yes. So
very challenging, very nice formula should be.
So I think you can try to expand this type of kernel function in terms of eigenfunctions in x variables and y variables. Product of this type of Cauchy type formula should also be somewhere, but yes, you cannot. Yeah, it's a difficult question.
No, I don't insist that it is easy, but it's just
just a bit, but it's a very good challenging program. Yes,
it's very challenging and very intriguing.
Interesting. Yes, I think so. I agree.
It is like, you know, like in the Bessel case, it should kind of Clausen duplication formula, something like this.
Okay, I think we have to finish our seminar. Let us thank the speaker again.
Thank you very much.
And we hope to get slides, and we hope to get another seminar from Professor Noumi. So the next two seminars will be about the Penlevé equations, about non-abelian, and then about discrete Penlevé. So thank you.
Thank you very much.
Very much.